yeah, display, so you can just look at it on your computer there. But I met her last year.
Oh, excellent. Okay. All right. So is this a little bit better in terms of? I mean, I know it's still really small. All right. So thank you for the introduction. This is this will be a new experience for me. I have never given a talk without it projected behind me, but we'll do the best we can. And I think since that turns it into a little bit more of an informal talk, and also you can't see all of the images very well, just feel free to ask questions as we go. Also, if I can, I'll use the board to draw. University instructors don't really draw on boards anymore, so that could be a whole interesting challenge for me, but I might use that a little bit too, to show some of the animations that we were going to be looking at. All right, so with that, I think I'll just get going. So before I get into this talk, the topic of the talk, the title is Geology of Oregon's High Desert, and it really combines two things. Beautiful photos, most of which are from the Oregon Natural Desert Association's calendars. They have these gorgeous calendars that come out every year. So photos that feature local photographers, and this one here is Cathedral Rock by Greg Burke. That's the John Day, right? This will be a good test of all of our geography of central and eastern Oregon. So it combines these photos of places that many of you have probably visited with the geology of the area, and it kind of bounces back and forth between introducing the geology and then looking at some of the photos. The other thing that I want to just make really clear is it brings in some of the newer research of geologic research for Oregon and Central Oregon and the Pacific Northwest, but none of it is my research. I'm just presenting, something very similar to what an overview would be if you were to take a Geology of the Pacific Northwest or a Geology of Oregon course. So I certainly don't want to make it look like I'm presenting any of my own work here. All right, so with that, I think I have one more plug in here. If you're interested in geology, which you must be if you're still here after all of this, there is a fairly new organization called the Central Oregon Geoscience Society that myself and a few retired geologists, it turns out there are a lot of retired geologists in Central Oregon. So we started this group maybe 6 years ago or so, and this is a group that we bring talks to Central Oregon, where this month will be our last talk. This is just a screenshot of the website, but this month will be our last talk, and then we'll pick up again in September. So September through May, 4th Tuesday of the month. These talks are always free and open to the public, and they feature all aspects of geology from researchers from different universities, from the U.S. Geological Society, from other agencies in Oregon who are working on geology. And those are always free to attend in person or Zoom. You can just tap into those talks through Zoom. We also organize field trips. You do need to be a member to go on field trips, but there will be lots of field trips over the summer. And then we support K through 12 outreach, earth sciences in the K through 12 schools throughout Central Oregon. And we also fund undergraduate and graduate student research grants for research in Oregon, or any aspect of earth science research in Oregon. So if you're interested in geology, check out that group, Central Oregon Geoscience Society. All right, so an outline of this talk. We're going to be kind of bouncing back and forth between plate tectonics and what that means for Oregon, and kind of Central and Eastern Oregon in particular. And during that process, we'll look at subduction zones, continental rifting, hot spots. These are the tectonic forces that have really shaped Oregon. And then after that, we'll take a look through photos, unfortunately quite small, of how all this geology shapes Oregon's desert landscapes. And then there will be a test after that. So, all right. So this, if you can see this image, it's showing the state of Oregon, and it's showing geologic provinces of Oregon. And I know it's very small for everyone. And this laser pointer isn't even going to work, but it kind of divides up the state into these different geologic provinces, and we're right here in Central Oregon at the meeting of the High Cascades. I think everyone's very familiar with what the High Cascades, snow-covered peaks. We're also at the meeting point of this geologic province called the High Lava Plains. If you were to drive from Bend to Burns, you're driving across the high lava plains. Also basin and range. And if you were to drive from Central Oregon to, seems to be cutting out, to Reno or beyond, Lakeview, and then into Nevada, you'd be driving through basin and range, these mountain ranges that kind of run north-south. And here in Central Oregon, we're right there in the meeting places of these geologic provinces. And these provinces, others that are on the map that are hard to see because it's not on the big screen, are the Blue Mountains in northeastern Oregon, the Oahe Uplands in southeastern Oregon, the Columbia Plateau, kind of between Oregon and Washington border, the Western Cascades. There is a difference between the High Cascades and the Western Cascades, which we'll talk about a little bit in this talk, but I think not much. The Willamette Valley, the Coast Range, and the Klamath Mountains. So these have been recognized since the first geologic maps of Oregon were made. So many decades we've recognized these geologic provinces. But more recently, and this is another map of the state, and this shows ecoregions of Oregon. And more recently, ecoregions have been mapped out. And this is plants and animals that live in different parts of the state. And this, is going to have less effect than it usually does when it's on a big screen. But if I go back and forth between the ecoregions and the geologic provinces, I'm just going to have to, you're going to have to believe me, there's a lot of overlap in the shapes of what you see. Ecoregions have the coast, the Willamette Valley, the Cascades. Let's see, I think they have the West Cascades and the East Cascades, the Columbia Plateau, the Blue Mountains, Basin and Range, and the Klamath Mountains. So very similar to what we just saw. So even though the geologic provinces it's been many decades since those have been recognized, we can see that these ecoregions kind of overlap, and geology really shapes what plants and what animals exist in Oregon. And then that's kind of sets the tone for the rest of the talk in that we're re-examining aspects. The rocks out there in all those different provinces, they haven't changed. But our understanding of how they formed has changed over time. So we'll kind of examine some of that as well. And that gets into plate tectonics. So this tiny little image shows a map of the world. And if you can see some browns and some blues, you're seeing continents in the brown, and blues are the oceans. And then it might be difficult to see, but there are yellow lines kind of separating some of these sections, running through the oceans and even through some of the continents. Those yellow lines are plate boundaries. So if you think about the planet, the entire planet, there's in the interior of the planet, there's the core, the mantle, and then the crust, and that's everything we really know and see every day about the planet, right? We know some things about the internal structure of the planet and what it's made of, but we never encounter it. We're like creatures entirely of the crust. And that's just the very outer kind of edge of the planet. But that crust is a brittle material. It's all rocky material, and it's brittle, which means that it breaks. If it undergoes stress, it's going to break. And the mantle, the layer below it, is not brittle. It is ductile. If it is, if stress is applied to the mantle, it's just going to bend and flow. So because the crust is brittle, but it's on this sphere, this round planet, it has to be broken into pieces. You can't have a brittle material. It's like breaking up this table and wrapping it around a sphere. You have to break it in order to get it around the sphere, right? So those are plates. And those plates are in constant motion. And so those yellow lines are showing you the boundaries between plates. And the red lines, probably those of you up close can see the red lines, might be a little hard from the back, but those are arrows. And they're vectors. They're showing movement of plates. And they're not only showing the direction of movement, but also the rate of movement. So over here in the bottom, there's an arrow that's, an inch or more maybe in length, and it says 10 centimeters per year. So if you see an arrow about that length, and there are a bunch here on the Pacific plate, that plate is moving 10 centimeters per year. And that's something we can kind of wrap our minds around, right? Like geology oftentimes is dealing in millions or billions of years, and it's just really hard to just get a handle on that kind of time. But 10 centimeters per year, we can recognize that kind of movement. So we're sitting here on the North American plate. It's not moving 10 centimeters per year. It's moving much slower, but we are moving, and these plates are interacting with each other as they move. All right, so that's the global perspective. Now we're going to, let me back up just one more really quick. And even if this was big screen, you would have to really squint to see that there's this tiny little plate here in the Pacific Northwest off the shore or off the coast of Oregon and Washington and part of California and part of British Columbia. And we're going to be kind of jumping down, like scoping or zooming into that little plate. There's no arrow for it, and that's just because it's moving quite slowly. And so the arrow, if you put an arrow on it, it would basically cover up the whole plate. So we're going to be talking about that plate in the next few slides. But first, here's just another image that just shows, in this one we've been looking at a map view, the global view of plate tectonics, as if you're looking down on the planet. This is a cross-section, as if you were to cut through the Earth and see what happens when these plates interact. And it was actually drawn for our part of the world, for the Pacific, kind of the entire Pacific region. And it has a continental crust here and a plate subducting underneath it. We'll talk more about that in a minute. And then on the other side over here, it has another continental crust and a plate subducting underneath that. That represents Japan, or parts of the Western Pacific. And this represents us here in the Pacific Northwest. And in the middle, there's an area where hot material is coming up, and that represents the Hawaiian Islands. So we're going to kind of talk about all those settings in a little more detail. So this really was drawn to kind of represent what we experience here in the Pacific Northwest, and also to show the different types of plate boundaries, when they collide together, when they separate or move away from each other, when they slide past each other, all of those. So that's convergent plate boundaries, divergent plate boundaries, transform plate boundaries, and hotspots. And hotspots, we'll talk more about them. They're not a place where plates meet, but they're a large-scale global tectonic feature. So they're always included in the discussion of plate tectonics. All right, so back to that global perspective and that tiny little plate off the coast of Oregon and Washington, that is called the Juan de Fuca plate. And now, if for those of you who can see this, we've zoomed in to that plate. And so now we're looking at the Juan de Fuca plate offshore of southern British Columbia, Washington, Oregon, and Northern California. And this line here, kind of everything on that side of that line is North America. Sorry. And everything on this side of the line is the Juan de Fuca plate, until you get out over to like this side of the image, and then that's the boundary between the Juan de Fuca plate and the Pacific plate. Is there something do I just need to hold it really close? Is that, okay. I'll try not to breathe too heavily or laugh. That's hard. So this is showing, this very small Juan de Fuca plate is moving towards the east. The Pacific plate is moving towards the west, which means that they are on a collision zone. And everywhere along that boundary where those plates meet, that is what we call a subduction zone, because that Juan de Fuca plate is subducting underneath the North American plate at that boundary where those plates meet. So this process creates a linear range of volcanoes that run parallel to the subduction zone. And you can see that in the image. This is the subduction zone. It's offshore of our coastline. But parallel to it, you can see all this red. Okay, I'm holding it really close, but it's still kind of coming and going. Sorry. So all of this red indicates the Cascades. The red colors themselves aren't individual volcanoes. Instead, it represents all of the lava flows and ash deposits that have been created by the Cascade volcanoes. And hopefully you can see that even though there are, individual peaks, volcanoes, Mount Rainier, Mount St. Helens, down here in California, Mount Shasta, there are all these individual peaks of volcanoes. Maybe, can everyone hear? I mean, I'm really good at shouting, but can everyone hear? Okay, thank you. you know, when we think of the Cascades, we think of these peaks, these individual peaks, Mount Hood, the Three Sisters, Newberry Volcano, maybe south of Bend. This is actually showing all of the lava flows that those volcanoes have produced. And so even though there are quite large volcanoes throughout the Cascade Range, if you look at the amount of lava that's been produced, Central Oregon is really like the most active section of the Cascades. Hopefully everyone can see there's a lot of red in Central Oregon. And there's kind of a cluster of a lot of volcanoes there. So we actually live in a very active section of the Cascades. All right.
Okay, Danielle?
Yeah, that's totally fine. Probably better for everyone else. For the tiny little pictures that you're all looking at. All right, so that was a map view. Now we're going again to a cross section. So this is looking at depth at the subduction zone. So the Juan de Fuca plate is coming in west of us. It's moving east and it's colliding with North America. Here's North America. And in that process, it is pushed down into the mantle. And the reason for that is the Juan de Fuca plate is an oceanic plate. Oceanic plates are made of basalt. And we are very familiar in Central Oregon with basalt. There's a lot of basalt on the continents, and particularly here in Central Oregon. But oceanic crust, oceanic plates are made entirely of basalt. There really isn't a lot of other types. There might be other types of rock, but they're chemically very similar to basalt. They're heavy and dense. Whereas on North America, where we're sitting today, there's plenty of basalt around, but there's also a lot of other types of rock. And if you were to kind of grind up all that rock and analyze the chemical composition of the entire continent, it would be a very different chemical composition than basalt, and it would be much lighter, less dense. So when those two plates collide, the oceanic plate is always forced underneath the continental plate. It's a density issue. So that's what this image is showing, is the Juan de Fuca plate subducting beneath North America. In this image and with my hands, it's kind of a two-dimensional image, but you have to imagine that plate, that Juan de Fuca plate, is coming out towards you. It's a big slab, and it's going towards the screen. So it's not just one place where that plate is touching the North American plate and subducting. It's this whole three-dimensional area. And as that Juan de Fuca plate gets deep enough, the pressure increases and the temperature increases, and the plate does not melt. There are textbooks, old textbooks, but sometimes, unfortunately, even new textbooks that show the plate melting, and that is not what happens. Instead, the plate just continues to subduct and get just recycled into the mantle. But in that process of going deeper and deeper into the earth, temperature increases, pressure increases, and the minerals in the rock of the plate are no longer stable. Those minerals were formed on the surface of the planet during volcanic eruptions. And rocks that cool on the surface of the planet have minerals in them that are happy at temperatures and even more so at pressures that are at the surface. And if you stuff them down into the mantle where pressure is much higher, they are no longer happy, and they change from one type of mineral to another type of mineral. So these are chemical reactions that are happening in the rock of the subducting plate. And the result is that hydrogen and oxygen is released between my hands here. That's the mantle. Here's the Juan de Fuca plate subducting. Here's the North American plate. Everything in between is the mantle. The mantle is not molten. It's solid. It's capable of moving and flowing, but it's a solid material. But if hydrogen and oxygen gets introduced into the mantle, that changes the melting temperature of the mantle. So just by having a subduction zone, having chemical reactions occur in the minerals of the rock, creating hydrogen and oxygen that gets into the mantle, just in that process you can cause melt to occur. And that melt will rise up and feed volcanoes. So an analogy of that kind of sounds like maybe it might be magic, but it's not. An analogy is on a cold day, which seems so long ago after these couple days. And there's ice on the sidewalk. You go out and sprinkle salt on the sidewalk. You didn't change the temperature outside. You didn't cause it to heat up outside. You didn't change the pressure outside. All you did was change the chemical composition of the ice. It was frozen water, and now it's frozen water plus salt, and that has a different melting temperature, right? So it melts just because you've added salt. So in this process, subducting a plate, releasing hydrogen and oxygen into the mantle melts just because water has been added. And it's not water as we know it, it's hydrogen and oxygen we call that H2O, we call it water, but the pressure down there is so high and the temperature is so high that it doesn't exist as liquid water. Okay, so that melted material rises up and feeds volcanoes. So again, think in 3 dimensions. You have this slab of subducting Juan de Fuca plate going all the way to the back of the room and all the way to the front of the room. And at the right depth, melt is going to occur and rise up. That means that there's going to be, here's the slab of subducting material, our 3-dimensional slab, and parallel to it is a mountain range where that melt rises up and feeds volcanoes. And that's why the Cascades runs north-south everywhere parallel to this subduction zone. All right, so I think we've probably covered, I'll just do this one slide, and then, and so that process generates volcanoes. That's why we have volcanoes in the Pacific Northwest. It's why we have active volcanoes in the Pacific Northwest. None of them are erupting right now, but they could erupt in the future because magma continues to be generated. It's also why we can expect very large earthquakes in the Pacific Northwest. And this image is it's a picture of the 2011, is that right? Tsunami in Japan, 2010 or 2011?
11.
Okay, thanks. There was a big earthquake, and that triggered a tsunami, and so that you probably all remember this event. And so this is just a picture of that. Our subduction zone here in the Pacific Northwest is very similar to that subduction zone in Japan. So not only does this process create volcanic activity, but also seismic activity. That's a topic for another talk. Okay, so that was like maybe half a term of intro geology. Are there any questions before we look at some pretty photos of what subduction does?
Is 10 centimeters like 3 or 4 inches? What is it?
4 inches.
Yeah.
Okay.
Yeah.
I was just wondering how fast it was moving.
Yeah. And some of the, and that's a pretty fast moving plate. Another way that that's often given in kind of human time scales is about the rate that your fingernails grow. Maybe a little, depends on your fingernails, and it depends on which plate you're looking at. But that, I feel like I have to cut my fingernails all the time, personally. So it is, again, like, it's a human time scale. Yeah.
How long has science been aware of tectonic movement, plate tectonics?
Since
Aristotle, or just...
No, so that's a great question. So this global picture of plate tectonics, this only really came about in the 1960s, 1970s. And it had a couple of different reasons for why it came about. One was World War II, and we were doing a lot of mapping of the ocean floor because we wanted to know where submarines were. And so we needed to map especially German submarines. So we wanted to map the ocean floor and figure out where the hiding places were for submarines. And when we mapped the ocean floor, we saw these underwater mountain ranges that really are, for those who can see this plate tectonics image, this boundary between plates, this divergent plate boundary where 2 plates are moving away. There's really underwater volcanoes there. So mapping that was really one reason why we started to, I wasn't around yet, and I did none of this work, but we as people, we as scientists, started piecing together, sort of clues from mapping the seafloor, creating bathymetry maps for the seafloor, taking samples from the seafloor, figuring out it's all basalt, and not only that, but it's really young basalt right here, and it gets progressively older and older and older in a mirror image pattern on 2 sides of what we will later figure out is a divergent plate boundary. That means new material is coming up and cooling and forming basalt and pushing those plates apart, and so the oldest material is going to be, way out here, and the youngest right there at that boundary. And then there's a lot of other science that was going on, that lots of different sort of ways of looking at evidence worldwide, and it all was pieced together to form this sort of overarching theory of plate tectonics. And it is a theory, but theory in science is used for something that really has a lot of supporting evidence, multiple lines of supporting evidence. It's not used in the way that we tend to use it in just everyday speech, like, I've got a theory. It's not a guess. It's not a hypothesis. It is a result of many hypotheses that have been studied and published, and it just represents thousands and thousands and thousands of papers. So that's what a theory is, and this is something that really came about as a theory not until probably the 1970s, and it is in progress in the 60s. And here in the Pacific Northwest, then in 1980, something happened. Yeah, Mount St. Helens erupts. So we just kind of pieced together this theory of plate tectonics, and then we get a volcanic eruption in the Pacific Northwest, and that really made local scientists in the Pacific Northwest ask, well, is the Cascades then still an active range, and is there still subduction occurring here? So this really changed the entire nature of geology, this theory of plate tectonics.
So that leads to my question, which is, if you know how fast the plates are moving and subducting, do you see any regularity in the Mount St. Helens events, the Mazama Mountain event, or anything?
No, so they don't follow. You may encounter sort of these average times between eruptions, and it's usually for the Cascades. It's usually I think it's about 60 years or something like that. But that is an average. They don't follow a set. There is no kind of regularity. So there doesn't seem to be any kind of, all right, so there's subduction, that plate is down there, it's generating magma, and the magma bodies are coming up and feeding volcanoes, but there doesn't seem to be regularity in how that process happens. It's probably happening continuously, and a lot of that magma is never making it up to the surface, it's just cooling in the earth. And then now, currently, people spend their entire career studying, okay, what about the ones that do get to the surface? Why did they get to the surface? What is the mechanisms? It's degassing, it's usually, or the vesiculation of gas. And that's again another topic of another talk. But there doesn't seem to be any like cyclical aspect of that. If that answers your question. Yeah. Okay, there's a question in the back, and then I'll come up and do these two.
I've heard that the idea of plate tectonics was actually around quite a bit earlier, but it wasn't generally accepted.
Yeah, so there was an earlier theory in kind of this is like testing my, because I always have slides, so this is kind of like 1914 time period, something like that. If anyone knows, or if you like have Siri up or whoever you can fact check me, please, because that's helpful for this kind of thing. But there was an earlier idea called continental drift. It wasn't plate tectonics, it was continental drift, and that was, if you look at a map of the continents, it really looks like they fit together, right? Like puzzle pieces, especially like Africa, the west coast of Africa and the east coast of South America. I mean, they just fit together, and you can see that all over the planet. Not only that, but there are similar rock types on these. Like if you did put all the continents together, the rock types match as if they used to be joined, and the fossil types match. And so there was a German meteorologist, Alfred Wegener. I never know how to say his last name. I don't speak German. Wegener. Kind of great explorer, sort of meteorologist, but interested in lots of different aspects of natural history and Earth history. And so he proposed this theory of continental drift. And at that time, there was a lot of competition in science, in earth sciences, in particular between Europe and North America. And so in Europe, it was, okay, maybe let's look for evidence of that. And in North America, it was absolutely not, you're crazy, that can't happen. And if it did happen, you need to provide a mechanism for how the plates have moved. And he couldn't provide the mechanism. He didn't know how they moved. It just really looked like they moved. And so that theory was, oftentimes it's sort of, recorded in geology books or history as that theory was just sort of shot down. I think that's a North American perspective. It was very much shot down on this continent. But even worldwide, it just didn't gain traction because there was no mechanism to explain it. And so it wasn't until the 60s that our technology improved that we could come up with this mechanism, and that's seafloor spreading. If you spread apart the oceans, you're essentially, the continents are just riding on the back of oceanic plates, right? And so you're separating plates that way. Okay, so there's a question up here. and
Yeah.
then back.
Oh, yeah, well, I had a question about the location of volcanoes in the Cascade chain.
Yeah.
And I've often wondered why, you know, the plate is like a continuous, like a belt almost, a plate that's
Mhm.
subducting. But the volcanoes are 40, 50 miles apart.
Mm-hmm.
And then the one that really puzzles me is that Mount St. Helens and Mount Adams are almost exactly east-west of
Yeah.
each other, and they're 50 miles apart.
Yeah.
How does that work?
Yeah, so again, this is something that people are spending their, currently spending careers trying to piece apart and answer these questions. And it does seem that there are these long-lived volcanic centers, like Mount Rainier and Mount St. Helens and Mount Adams and Mount Hood and Mount Jefferson. If you think of the big volcanic peaks, those are long-lived. They've been producing magma for, probably in the million-year range. And so there does seem to be these preferred pathways of magma. So the question there is, how do those get established? Why does that become a preferred pathway for magma? And people are trying to answer those questions. The other is it's not totally a straight line, and there is a curve to the subduction zone. Oops, I'm going backwards. It's hard when you're looking at it upside down. So it is not totally a straight line. It kind of curves a little farther to the west up by Vancouver Island. And so that kind of explains why Mount St. Helens sits a little farther west. There is an actual curve in that pattern of subduction, which means that the volcanoes at the surface are going to have a curve in it. But Mount Adams sits quite far east of the axis of the Cascades, and so does Newberry Volcano, south of Bend, and Medicine Lake Volcano in Northern California. And so those are also questions that people are working on, and we'll get into a little bit of some of the potential answers for that. So I don't have an answer for either of your questions, but this is, these are questions that people ask and haven't fully pieced together yet. Another kind of just really interesting side note on the long-lived pathways of magma, and I mentioned those volcanic peaks, Mount Hood, Mount Jefferson, the Three Sisters. Not only have those centers been kind of long-lived and built up these big volcanoes, but if you just go west of each of those peaks into the old Western Cascades, which is a much older version of the Cascades, there are old granitic rocks that represent a much earlier version of Mount Hood and Mount Jefferson and the Three Sisters. So that's been a preferred pathway for magma for millions of years. So kind of interesting and intriguing. Okay, there's a question in the back, and then we'll move on.
What kind of instruments do they use to measure a subduction?
Yeah, so mostly to measure the movement of the plates on the surface of the Earth, GPS.
Okay.
Mostly it's GPS. And GPS is super sensitive. You can install permanent GPS stations and be continuously collecting GPS data. And so that has been actually a really interesting kind of progression of the theory of plate tectonics is, in the 60s and 70s and 80s, there was a lot of, well, if this is all correct, then we should see some movements like this. And it wasn't until we had GPS that could actually be tested. And sure enough, we are seeing those movements. So here in the Pacific Northwest, where we have a subduction zone, we should see movement of the Juan de Fuca plate this way and the North American plate this way. But not only that, we should see in that place where they meet, we should see some uplift because there's stress building up at that location. And we do. In the Coast Range, we can measure with GPS not only the direction of movement this way, but also the direction of movement this way. So GPS is one example, and then there are others. We now have very sensitive seismic equipment, so we can measure if you have a subducting plate, you should have deep earthquakes because that plate is brittle and cold and it's going into the mantle. The rest of the mantle is warm and ductile. If it breaks, or if it is if stress is applied to it, it will just bend. And bending is not an earthquake. Breaking rock is an earthquake. So if you have cold, brittle material going down into a subduction zone, stress is involved in that movement, and you should have deep earthquakes in the subducting plate itself. And now we have, very sensitive seismic equipment, and we can measure deep earthquakes in the plate itself. So those are just a few examples.
Are they predictive, the deep earthquakes?
Are they predictive of?
Of real earthquakes that we would feel?
There is a lot of work actually happening now along the Cascadia subduction zone of these earthquakes, not necessarily the deep ones, but something called slow earthquakes or silent earthquakes. And those are earthquakes that are generated here at that, at the place where the two plates are meeting, and they release the same amount of energy as like a magnitude, it varies, kind of 4 to maybe 6 or 7 earthquake, but instead of doing it all at once, they do it over weeks. So that's why they're called slow or silent earthquakes, is we would never feel them because the energy is being released much more slowly. But there's a lot of thought that they could be indicating, they could help us try to predict when the next big Cascadia subduction earthquake is. And there's a lot of current research. If you're interested in this kind of stuff, really check out that Central Oregon Geoscience Society, because we bring in researchers who are working on these topics. There's a lot of questions about, okay, do those silent or slow earthquakes help release stress along the entire subduction zone, which would be good, right? It would mean that if stress is being released, it's not being built up and we won't have a giant earthquake. Or do they actually add to the stress? And unfortunately, most of the research right now is pointing to that they add to the stress. But that's another, you guys are all asking great questions of just ongoing research, which was kind of what I wanted the topic of this talk to be, so that's great. Doesn't mean we get any answers, but at least you know what earth scientists are doing. Okay, so some pretty pictures of subduction in Oregon, and these are going to be, obviously hard for you to see, but you may have thought, if I'm going to talk about subduction of Oregon and subduction of the Juan de Fuca Plate and magma generated in the Cascades, I would show pictures of the Cascades. But instead, what is up here is a picture of Spring Basin Wilderness Area by Jim Davis, which is in the John Day area. So maybe not what you were expecting for a picture of subduction. Oregon has been shaped by subduction for millions of years. This has been a process that has been going on since long before the Cascades existed. The age of the Cascades is about 40 million years for the old Western Cascades, and the High Cascades, it's about maybe 5 to 10 million years to today, to the present. But we have had subduction in Oregon for millions of years before that. And the Clarno volcanics, if you've heard of Clarno Formation or Clarno volcanics, this is like in the Ochocos and in the John Day area. There was a range of volcanoes very similar to the Cascades in kind of 54 to 39 million years ago. So Oregon was a very different place at that time, but we had some version of Cascade-like volcanoes. All right, so another picture of Sutton Mountain, again, Sutton Mountain Wilderness Study Area, and this one looks really similar to the Painted Hills. It's not in the Painted Hills, but it's adjacent to the Painted Hills. So these ash layers of these volcanoes that were in existence during that time period. Now we're a little younger. We were talking about what we today call the Clarno Formation, which is 54 to 39 million. Those ash layers that you see in the Painted Hills are in what we call the John Day Formation, which is about 18 million years to 39 million years. So we've had like millions of years worth of different versions of something like the Cascades. And then we get a little closer, actually very close to where we are right now, and the packet of rocks called the Deschutes Formation, which is exposed beautifully in the canyons there and there, in the Crooked River and the Deschutes River. And that's about 75 to about 4 million years. So these are rock layers that are fully from the Cascades. Now we have like something, it's not the Cascades we know and love today. There's no Mount Bachelor, there's no Three Sisters, there's no Mount Hood, but there are versions of volcanoes that are in roughly the same place, and they're producing material that comes off to the east and fills up the Deschutes Basin, and then these rivers erode through and expose them. And then this is Newberry Volcano, which is about 400,000 years. So now we're getting into the current, not just the Cascades, but the volcanoes that exist now that we can look at in the skyline, depending on where you are. So Newberry Volcano is about 500,000 years in age, but I do say 400,000 years to present. And it really is. The last eruption at Newberry was 1,300 years ago, which geologically is just the blink of an eye. and it is very active. There's a magma chamber has been imaged below, below the surface. There are hot springs, there are gas emissions, all of their little earthquakes. All of this is very, very clear indications that volcano is still active and could possibly erupt. And then here's another picture of Newberry. This is the big obsidian flow, just a gorgeous sunset picture. That's the 1,300 year lava flow at Newberry. And then the Three Sisters, just a great picture of snow-covered volcanoes. And Broken Top. These are all kind of range in age from about 300,000 years ago to the present. Anyone know when the last eruption at South Sister was? I feel like I should have brought prizes and just in case. 2,000 years ago for that. For the last, and then there was another more recent about 1,600 years ago. The 2,000 year eruption was the Devil's Hill chain of vents, which if you're on the south side of South Sister and near Devil's Lake, there's a lava flow that goes right to the road. Roads and trails are well known for stopping lava flows. Just a volcanologist joke. Worldwide, lava flows stop at roads and trails, but not for the reason you think. But it does. It comes right down to the highway, and obviously the highway was built to avoid the lava flow. But that's a 2,000-year-old lava flow, and as you hike up towards Wickiup Plains, you hike past more of those 2,000-year-old lava flows. And then on the northwest flank of North Sister, Collier Cone, the Pacific Crest Trail goes right through that area. Collier Cone is about 1,600 years old, so very recent eruptions. All right, so that was convergent plate boundaries, subduction zones. Now we're going to, and kind of some of the areas in Oregon where you see results of those. Now we're going to move on from where plates are moving towards each other to where plates are moving away from each other, divergent plate boundaries. And I'm not going to spend a lot of time on these images because it's hard for you to see them anyway. But just keep in mind that two plates are moving away, separating. This is one of those maps that does show bathymetry, ocean floor bathymetry, and if you could see it on the large screen, you would see these underwater volcanoes, and that is where these two plates are moving away from each other. And interestingly, that line here, let's see, where am I? Here in the Pacific Ocean, this is the boundary between the Pacific Plate and various other plates, and those two plates are moving away from each other, and that line kind of disappears right under Baja, the Baja region. And if you're familiar with Baja, it's a peninsula, and the reason why is because it's being pulled apart from North America. So right where these plates are separating, and then on land, in the oceans, the plates are separating. On land, the land kind of seems to be separating too. So we'll talk about some reasons for that as well in this divergent plate boundary section. All right, so this is, I really don't think I can do much to recreate this. This is actually an animated section that shows the subduction of the Juan de Fuca plate. And because it moves and you won't be able to see it, I'm not even going to try. But basically what it is showing is that this divergent plate boundary, we're all gonna have to think in not 2 dimensions, but 3 or 4 dimensions. So picture this divergent plate boundary where the Pacific plate and the older version of the Juan de Fuca plate are pulling away from each other. So just out offshore in the Pacific Ocean, those two plates are moving away from each other. And over here is North America, let's say the table. So up here where you guys can see it, here's North America. And the Juan de Fuca plate is subducting under North America, but also there's this divergent plate boundary between the Pacific plate and the Juan de Fuca plate. Is everyone good? Everyone's following me? So these plates are moving away from each other, and this plate is subducting between this North America, but this whole thing over here is also moving this way. Plates can move in different, an analogy for this is like if you're on a plane and you're flying to New York, you're going east, but if you get up and walk to the back of the plane to go to the restroom, you're walking west, but the plane is taking you much faster east, right? So you have multiple directions of movement going on at different rates. So same thing is happening here. The Juan de Fuca plate and the Pacific plate are moving apart from each other, but the whole thing, as they move apart, the whole thing is going this way, which means that when the whole thing moving apart gets to North America, the whole moving apart bit subducts. Everyone picture that? Crazy, I know. So now, from our perspective on the surface of the Earth, if we're standing here on North America, a divergent plate boundary has just disappeared underneath us. And it's going to keep moving underneath us. So that's what this image is showing you. Hopefully I kind of recreated that. And what this image eventually ends up doing, or this animation, what it eventually ends up doing, once that divergent plate boundary disappears beneath North America starts to thin and pull apart. And the west part of the North American continent, like the Nevada region and parts of Oregon and California, start to get thinned and stretched, and they actually increase in area. They were a narrow region, and they get pulled and stretched out to a much wider region. And this is Great Basin. This is what is happening to cause what we call the Great Basin part of Western North America. It's being pulled apart. It was a much kind of thinner section, and now it's been pulled and stretched to a thicker section. All right, so I'm sorry, you can't see the animation. I'm running it for the people who are in the front row. Once that divergent plate boundary subducts beneath North America actually starts to stretch apart, and the states are outlined on there. In Nevada, there were no states at that time, but Nevada has actually pulled out. It was a narrow little section, and it's actually been stretched out. So this is what causes the Great Basin region of Western North America, and this is just a map that shows that part of Western North America. It's sort of centered in Nevada, but parts of it come up into southeastern Oregon, and most of Eastern California is all part of this pulling and stretching. So this is not a divergent plate boundary. This is fully all on the North American plate, but if it continues to pull and stretch the North American plate, it would break it up into two plates. So we have kind of like a new, like a predecessor of a divergent plate boundary happening in our own backyard. And the pulling and stretching has pulled the Baja Peninsula away, and it has kind of pulled the Death Valley region, and that's why it has kind of dropped lower than the rest of the continent. All right, so this is just showing that type of force pulling apart on a continent and the type of faulting that occurs in that. You can't see this image, but what it's showing you, well, I'll wait until we get photos, because there are real photos of Oregon that show you what type of topography is created in this process. So let's see, that's also it's just too small to see. It's just showing where in Oregon the faults are. But we're just going to take a field trip to where those faults are. So now we have an image of kind of the predecessor of a divergent plate boundary right here in Oregon. And this one is the Pueblo Mountains, which are in southeastern Oregon. And from about 15 million years ago to today, this type of pulling and stretching has caused faults to form those mountains, the Pueblo Mountains, near the Nevada border. This is Mickey Basin in the Alvord Desert region, and if you are familiar with the area, or you can kind of see this image, there are these fault block mountains, high topography, and then low topography of the Alvord Desert, and that's what's created in this type of pulling or thinning of the crust.
You're talking about Steens Mountain?
Yeah, Steens, and now here's a picture of Steens itself. This is Big Indian Gorge. Big Indian Gorge itself is not part of faulting. We're not looking at a fault. These faults do create low and high topography, but Steens Mountain as a whole is this big fault block. If you kind of go up on the western slope, the western slope, you go up, gradually, and then on the eastern side, it's just like shoots down thousands of feet to the Alvord Desert, right? That is the fault itself. The Alvord Desert was dropped down, the Steens block was kind of thrust up, and because it's up so high, it was glaciated. And so Big Indian Gorge is actually glacially eroded. But Steens Mountain itself is this high fault block next to a down-dropped block. Very similar to this, which is Abert Rim, high block, and then Lake Abert, low, dropped down block. And that is the fault. Like that line with that really steep cliff face is the fault. So when you stand at the base of Abert Rim, you're on that fault. And the lake part dropped down, and the rim part was kind of pushed up during this pulling apart of the crust.
And
Yeah.
I do have another connector. If you wanna try that TV screen one more time with that
Sure.
HDMI port that's on that connector.
Sure.
Might take us a couple of minutes to,
Well, you
switch
probably,
gears
okay,
and
so I
set
was
it up.
actually just, in a few more slides, I was also going to say, we've had some delays. If you need to go, you can also go. We're a little behind schedule. I'm happy to keep talking, but I did want to give people the option to leave. And so maybe as we try this, you can sneak out without, hurting my feelings. No, I won't be hurt at all if some of you decide to go, but you might want a little bit of a break.
or a break.
Yeah. Okay, let's try this.
So,
Thank you. Okay, so I've gone back a few slides from where we were. So we were talking about pulling apart of a continent, and this is the type of faulting that occurs in that setting. So we call that here in North America, we call it basin and range, and we've named the Great Basin for that. In other parts of the world, they call it Horst and Graben, and the Horst is what we call the range, the high part, and the Graben is the low part, what we call the basin. Those are German terms. But it's the same process. It's the type of faulting that results when you pull apart or stretch the crust. And so this is a map that I didn't spend a lot of time on because you guys couldn't see it. But this shows major faults in Oregon. And it's not all the faults in the state, but it's some of the major faults in the state. And these north-south, or roughly north-south running faults are those basin and range faults. It's what you see repeated over and over, lines like that throughout Nevada and throughout eastern California, parts of Idaho, parts of Utah, but also southeastern Oregon. And as a result of that, there are also northwest running faults. And there was a question, I think the person, did you ask about crack in the ground? She left, yeah. So there's a question about crack in the ground in Christmas Valley. And crack in the ground is essentially one of these northwest running faults. So part of the process of having this basin and range faulting in Oregon has also resulted in these northwest trending faults. And we'll see some ideas for the reason for that later on. So we have the early stages of continental rifting. We do not have a full-on divergent plate boundary pulling North America into two plates, but we have the early stages of that. And if we stick around for a few million years, maybe Western North America will be its own continent, which maybe some people would be happy about. I don't know. We won't be the people around to see that, but all right. So then just some pretty pictures of the Pueblo Mountains, the Mickey Basin, and here you can really see the range, the fault, and the basin. And you see it repeated over and over and over. There's a range, this is the steep side, that's the fault. That whole block is uplifted, and there's a basin adjacent to it. You can see it repeated here. So this throughout southeastern Oregon, you see these ramps and sheer sides. And that's like just textbook basin and range. Steen's Big Indian Gorge isn't that. That's glacially carved. But Steen's Mountain itself is something similar. We'll see pictures in a minute. This is Abert Rim. That's the steep fault, the rim itself, the downdrop basin where the lake is, and then the higher area of the range. And then this is a map of part of southeastern Oregon. The dashed lines are counties. So Lake County, Harney County, and then this is the California-Oregon border and the Nevada-Oregon border. And this is just showing there are these lakes throughout southeastern Oregon. And we still have some of them. Here's Summer Lake. Here's Abert Lake, which we saw pictures of. Malheur Lake. So the dark blue is the current extent of these lakes in a really good year. And the light blue is what it was like 14,000 years ago during the last glacial maximum, when the climate was cooler and wetter, and there were no glaciers really in this region, It's not like this is meltwater from glaciers.
No.
Or just need-
Okay, at least I know it wasn't my computer now. Okay, we'll just go with it. So it's not like this is glacial meltwater. Instead, this is just there's more rain, more snow falling every year, and so it's just wetter. And so streams fill into these basins. All these basins are down-dropped areas, and streams fill into there, and the basins fill up with water. And there's no outlet. That's one other great thing about the basin and range, or Great Basin, which everyone is probably familiar with, is that all that water stays. It doesn't make it to the ocean. There's only a few rivers that get water out of the basin and range area into the ocean. So all that water stays there and fills up these valleys. And so in 14,000 years ago, during the last glacial maximum, these lakes were huge. And today we have much smaller versions of them. And so this is what, now we have a great picture of Steens. So there's the fault block of Steens. That's the eastern side that is very sheer. The western side is just this gradual block. And Albert Desert is the downdropped part of the fault. Steens is the upthrust part of the fault. And that was a lake. And now we just have this lake bed because we're in a drier, warmer climate. And another great picture of the same area. All right. So now this is just kind of, putting this together and how have these different types of plate movements shaped Oregon. And now I think you guys, you'll get to see the animation, but I think it's not linked because now we're not on my computer anymore. So I'm just going to really quickly go to the animation. Sorry. It's worth it though. You'll like it. This one. Hopefully it plays on your computer. It might need to be adjusted. It looks like it's gonna. Okay, so in the slide, which is behind here, I've said, how do these plate movements shape Oregon? And there's some other text that is covered up that you can't see. That the easy version of plate tectonics, the simple version is these plates are moving and they're interacting. They're colliding with each other, they're separating, they're sliding past each other. That's the simple version. But the truer and more complex version is that plates don't always move as one unit. The North American plate the whole plate isn't always going in the same direction. And that's especially true of a plate like North America, where the whole western edge of the plate is new stuff. It's been added on over the last 200 million years. That's pretty new, given the age of the planet. So the original boundary of the North American plate, the original edge of North America, was kind of the Oregon-Idaho border. And everything west of that has been added on. It's all younger material. And that's true not just for Oregon, but for the entire North American continent, all the way from Alaska to Central America. So all that new material added on, it's not part of the original stable old plate, and it's going to act a little squirrely when these big plates like the Pacific plate and the North American plate are moving. That stuff on the edge is going to be a little bit funny. And that's not true on the east coast of North America. The east coast is all old original North American plate. It's going to move as one unit. But here on the west coast, it's going to go a little weird. So I'll start this animation, and you'll see the directions of movement. The Pacific plate's moving this way. The Juan de Fuca plate's moving this way. There's not an arrow from the North American plate, but it's roughly kind of colliding, going the opposite way of the Pacific plate. And when we start this, that was the old last little bit of subduction. And now, as the Pacific plate drags across the North American plate, it drags pieces of the North American plate with it. This is the San Andreas Fault, that red line. And so there is actually land on the west side of the San Andreas Fault, and it's getting dragged north with the Pacific plate. And then there's even some pieces that are getting rotated because they're kind of caught between the stable part of North America and this part that's getting dragged by the Pacific plate. So the movement of the Pacific plate dragging along North America impacts the edge of North America itself. And the reason is North America is made up, that western part of North America is made up of these individual pieces of old islands and small continents that were added onto the edge of North America. That's kind of a subject of an entirely different talk. I don't want to gloss it over, but it's also kind of too complicated to get into here. And so you can even see, if you're familiar with the transverse range in California, you can see how that forms. It's a mountain range that originally, it should be going north-south, but it's been rotated clockwise by this dragging of the Pacific plate, and so it actually goes east-west. All right, so plate tectonics is messy. It's not always nice and clean.
What mountain range was that you said?
The transverse range.
Transverse range.
So that means I'm gonna keep it out of full mode for a minute because we're gonna watch another animation. So because plates don't always move as one unit, some plates consist of these individual blocks that move at different speeds. That's going to impact Oregon. We saw what happens in California, but it's also going to impact geology in Oregon. And so this next animation shows that. And we'll spend a little, we'll go through this one just a few times, I think, which like we did the last one. All right. And this is really kind of, the focus of this talk was like new understandings of the geology of Oregon. We've seen the rocks since those first maps showing the geologic provinces were made, in the 1930s, 40s, 50s, 60s. People were mapping Oregon and mapping out the rocks, but now we have a much better understanding of those rocks. Oh, this is like the best part. I hope it comes back. But wow, oh, there it is. Okay, so I'll play this before any shenanigans start. So we're gonna, again, there's directions of movement. The Pacific plate is moving northwest. The Juan de Fuca plate is moving east, a little bit northeast. We have basin and range kind of pulling apart in North America, so that provides a force that's moving towards the northwest. And then North America itself is moving kind of southwest. So lots of directions of movement all at the same time, way more complicated than the airplane going to New York and you go to the restroom. This is like many directions of movement happening all at once. And we're gonna start here with the Pacific plate, sliding along the San Andreas Fault and bringing, kind of deforming the west coast of California in that process. And you already saw an animation for that. Now we're going to look at, instead of the transverse range, which was rotated during that process, we're going to look at the Sierra Nevada block. And the Sierra Nevada block is exactly what it sounds like. It's the Sierra Nevadas. It's solid, cohesive, beautiful, gorgeous granite. And it's all pretty much one unit. And so when the Pacific plate drags parts of Western California along with it, the Sierra Nevada block is going to come as one unit. It's not going to separate into these different blocks. So here we'll start it, and you can see as the Pacific plate moves north, the Sierra Nevada block also moves north, and it pushes into this pink block. And the pink block is basically the basement rock of the entire Puget Sound and Willamette Valley, and it's called Silesia. It was erupted as basalt lava flows underwater off the coast of Oregon, and it got kind of added on. It's now part of Oregon. It's not part of the Juan de Fuca plate. It never really was. But now it's like fully on land. It's just buried by other rock types. So when you're in the Willamette Valley, somewhere down there below you is Silesia. A lot of basalt. It's almost entirely basalt. And because it's basalt, which is also a solid, cohesive rock, when the Sierra Nevada block pushes up into the pink block, Silesia just pushes up to the green block. It's not going to rotate and do these squirrely things and break apart because it's all solid, cohesive basalt. So here you can see, there goes the Sierra Nevada block chugging away to the north. It pushes the pink block, but it moves to the north as one unit, and the Seattle area, which is in the green, gets shortened. It gets squished because it has these two blocks shoving it from the south, and the beige area is all original North American plate. It's not going anywhere relative to what all these other things are doing. So that green area is getting squished or shortened because it can't move this direction because that's all solid North American plate, and it's getting pinched but from the south.
What's the blue?
I'll get to the blue in a minute. Before that, just really quickly, if you're familiar with Seattle and faults in Seattle, they all run east-west. And that's why, because if you push from the south to the north and shorten that green block, you're going to create east-west running faults. It's like pushing a rug and the rug buckles like this. And those are the hills in Seattle and the faults in Seattle. Okay, so I'll play it again, and now we can watch the blue block. And the blue block is kind of like the Yakima area, and then some of the Blue Mountains and Columbia Plateau in Oregon. So kind of like the Dalles and a little further east of that area. Does that make sense? Mm-hmm. So we'll play this again, and now watch what the blue block does. It actually rotates a little. It's moving north, and it's kind of rotating a little bit. Oh.
Use the cursor, keep moving the cursor.
Yeah, I did that. That was the first thing I tried when this happened with my computer. All right, so the blue block is it's similar to the green block. The blue block is getting pinched or shortened because it also has solid North American beige up there. And if you've driven, it's just spectacular. If you drive Highway 97 through Yakima to Ellensburg, and the freeway, you're on a freeway at that point, right? It's like 4-lane freeway, and it's going up and over these massive hills. Like, why is it built that way? And that's the Yakima Fold Belt. That's the same as those fault lines going north-south in Seattle. It's the result of that whole blue area getting pinched or squeezed. And then also, I'll play it one more time, and now look at the orange, which is the Cascades. So all those little triangles represent volcanoes. And there are the old Cascades. And as all this movement happens, they have rotated. And now there's new volcanoes coming up a little bit to the east. So these volcanoes, the old Western Cascades were here. They rotated this way. And now these are this and this, that represents the volcanoes that we know today, the high Cascades. So that is kind of the main difference between the Western Cascades and the high Cascades. The high Cascades are a little farther to the east. The Western Cascades were located in the same place, but they've been rotated clockwise. And you can actually see that. You can see the dashed line where they were, and they've just pivoted clockwise. And that means that when subduction is occurring and magma is being generated, that magma rises up, feeds volcanoes, but those volcanoes have rotated off the area where magma is produced, and new volcanoes have come up to the east. So that's the difference between the Western Cascades. And that's why the Western Cascades are extinct. They are no longer located over the place where magma is being produced. There's a question.
Is there any GPS evidence of the Columbia Gorge getting skinnier?
Yeah, there is. That's a great question because it leads exactly. Oh, I have to go. I'm not in the PowerPoint. It leads to the next slide. Slideshow, come on. Okay. So we watched all of this stuff, and now there's the GPS evidence for all of it. And you don't see the shortening, but you can infer it in the GPS data. So what you're seeing here is if you see a blue arrow, they're a little fuzzy, I'm sorry, but these are all blue arrows and red arrows. There's the head of the arrow and the tail of the arrow. The blue arrows are GPS surveys. So people have gone out with a really, not your basic handheld GPS, but a really sensitive GPS equipment. And they've gone and walked surveys and collected data. And then the red arrows are permanent GPS stations. So everywhere you see a red arrow, these red triangles are volcanoes. But everywhere you see a red arrow, there's a station there now constantly collecting data. And again, these are vectors, kind of like what I was showing for the movement of plates. The direction of the arrow indicates the direction of movement. These arrows on the west coast are kind of all pointing this way. And the length of the arrow, up there's a black arrow. And if you see an arrow that long, that represents 10 millimeters of movement per year. And some of these arrows are twice that length or more. So again, this is like, we're sitting here in Oregon and we're rotating in some places 10 or 20 millimeters per year clockwise. So you can see that this rotation is kind of centered somewhere around here, and this clockwise rotation has occurred for millions of years, which means there's more rotation here on the coast of Oregon and Washington, less, yeah, see, mouse doesn't do it. Less in southern Oregon, more in northern Oregon, and even more in Washington. Less as you go east, less rotation as you go east. And if we go back, you can actually see that kind of puts the pivot point somewhere kind of in the Columbia Gorge, in the eastern part of the Columbia Gorge somewhere. There's some debate among different people as to where that pivot point actually is. And so because of this GPS data, you can't, in just looking at this, you can't tell, oh, Washington is getting squeezed, it's getting shortened. But if you actually look at the direction of movement for those areas in the Yakima Fold Belt or in Seattle, you do see that.
Yeah, it looks like it. I mean, that's almost proof, right?
Yeah, yeah. So this rotation of Oregon and Washington, this is something that was, first kind of identified probably about 20 years ago. And since there's been more and more work really building on it. And it has done, for our understanding of the geology of the Pacific Northwest, this has done what plate tectonics did for global understanding of geology. This just really makes so many things fit. Like, why is there an old extinct Western Cascade Range and a younger high Cascade Range that's still active? So many of those questions are answered by this rotation of Oregon. All right, so now I think we're at another time, because it's a little break, we're going to talk about hotspots now. So if people wanted to leave, please feel free. I won't be offended at all, because you didn't really sign up for like a 3-hour tour of this whole thing. But I'll very briefly look at hotspots, and we'll look at some nice pictures of hotspots, much like we did with convergent plate boundaries and divergent plate boundaries, and then the talk is over. So again, hotspots are not a type of plate boundary, but they're very important tectonic features. And I mentioned when you couldn't see these images that here in the Pacific, there's this place where it's all one plate. That's all the Pacific plate. But there is this place where hot material is coming up from deep in the mantle, and it's causing volcanic activity at the surface. And that's, of course, Hawaii. It's not labeled as Hawaii on this because this is hypothetical, but it's drawn to be very similar to our part of the world here and the Pacific Ocean and Japan. All right, so let's kind of zoom in on just a hotspot by itself. So there's a lot of ongoing current research about hotspots and mantle plumes. The hotspot is the place on the surface where volcanic activity is occurring, but the mantle plume is thought to come up from somewhere deep in the mantle, and we can image the interior of the Earth, much like we can image the interior of ourselves using similar types of technology, but we don't fully have a solid understanding of, like, do these mantle plumes exist in the way that they're drawn here? And where do they actually start? Is it at the core mantle boundary, which is shown here? Or is it somewhere else in the mantle? Or do some of them start at one place and some of them start at another? These are all questions that people are researching now and trying to answer. So we don't know all that we would like about hotspots and mantle plumes, but we do know that there are places in the mantle where warm material is coming up. And remember the mantle, hot. It's not just warm, it's very hot. And remember the mantle, even though it's always drawn in oranges and reds, which indicate kind of that it should be molten, it's not. It's totally solid. It should be drawn in green. The mantle is green. It's made up of green minerals. And these all should be green as far as I'm concerned, but we've somehow got stuck in this, showing them in reds just because the temperature is higher. Anyway, it's not molten. This is solid mantle material, and it's hot, but it's solid. And this is also solid, hotter, but also solid mantle material rising up in it. And so that's one thing about geology. Not only do you have to wrap your head about immense periods of time and three-dimensional processes, but also that solid materials can move, they can flow. So this is solid hot rock rising up through solid hot rock. But it's a temperature difference. The rock rising up is hotter than the rock that it's rising through. Yeah.
Now you were talking about these conflicting areas. creating hydrogen?
At a convergent plate boundary where there's a subduction zone. Yeah, not in this setting.
Okay.
Only in this setting. And only because the minerals going down the subduction zone in the basalt of this rock, those minerals contain hydrogen and oxygen, along with a bunch of other stuff like iron and magnesium and silicon. And those minerals formed here at surface pressure, and they're not happy at high pressure. And so they undergo chemical reactions, they change to new minerals, that's metamorphism. They change to new minerals, and hydrogen and oxygen is released as a result, and that causes melting. At a hot spot, there's none of that. Nothing is being subducted, nothing is bringing hydrogen and oxygen into the mantle. Does that answer your... So the reason that melting occurs at a subduction zone is because hydrogen and oxygen has been released into the mantle. The reason that melting occurs at a hot spot is because hot material comes up relatively quickly through the mantle to the crust. And so it's going from very high pressure to still high pressure. We couldn't survive at the base of the crust. And we can't even drill down to the base of the crust because pressure just collapses everything, and we haven't been able to drill that deep anyway. Actually, I'll take that back. At an oceanic plate, which is maybe 7 miles, 5 miles thick, we can drill that deep, but we've never done it in an oceanic plate where it's thin. We've done it in continental plates, but continental plates are tens or hundreds of miles deep. So we can't drill down there. This pressure is very, very high, but it's lower, much lower than the pressure way down here in the mantle. And what happens if you lower the pressure on a material? It melts. Yeah. Because we're surface creatures and we don't deal in changes of pressure very much, even if you go from the coast to Mount Everest or the coast to the deepest part of the ocean, those are immense pressure changes to us, but they're nothing compared to the pressures in the mantle. So we think of temperature as being like the main control on whether or not something is a solid or a liquid, but pressure is just as important. And if you lower the pressure on a material, it will melt if you lower it enough, wherever its melting point is. So if you can move material from deep in the mantle to shallow in the mantle quickly enough, you're actually decreasing the pressure of that material, and it melts. As it comes up, it melts. Also, the temperature, because this material is rising quickly enough, the temperature of the mantle here is lower. It's still very high, but it's lower than the temperature of the mantle where that hot material has come up. You've actually brought hotter material up to the surface as you've depressurized it. And so because of those two things, the mantle melts in that location. It's hotter, and the pressure is lower. From the perspective of this mantle, the temperature is hotter, and from the perspective of this mantle, which rose up, the pressure is lower. So the combination of those two things causes melting. So you get on the surface of the earth this eruption of immense amounts of basalt lava flows. So think about like pictures of lava flows, or maybe you've seen lava flows in Hawaii, like rivers of lava flowing across the landscape. Picture that, but on a much larger scale, covering hundreds of square miles with just lava flow after lava flow after lava flow. So much basalt lava has erupted that they're called flood basalts, because they literally just flood the surface with lava flows. Nothing like this is happening on the planet today, but it has happened in the past. And we'll look at places where it has happened. So that's the initial kind of impact of that mantle plume getting to the base of the crust. But remember, the plate is moving, in this case, off to the left. So all of that, flooded area of basalt lava flows that's now solid rock, that all is moved on the back of the plate. And now there's still melting that occurs, but the head of the plume, which caused most of the melt, is now gone. It's just the tail of the plume, so less melt is generated. And so you just have volcanic activity, but the plate continues to move off to the left. So it's always going to be dragging those volcanoes away. The only active volcanoes are the ones directly on top of the hot spot. So that essentially was, that time did. So the only, these images are essentially showing Hawaii. And this is like what we have now. That the flood basalts have been dragged away, they're gone, but we have these chains of islands that are the Hawaiian Islands, and the activity is just on the Hawaiian Islands that are over the hotspot, which would be Hawaii, and maybe Maui. And then the other islands are extinct volcanoes.
Yeah, do you happen to know anything about, or is it known, if these hotspots have a life, or is there an origin and they die out, or are they more or less kind of like eternal? I mean, are they always present, or, you know?
They don't seem to be always present. I don't have it. I'm pretty sure I don't have it on this in this talk, but there are maps, global maps showing places where volcanic activity has occurred from hotspots. And in some of those places, like Hawaii, the volcanic activity is still occurring, so we think that's still present. But in others, there is no volcanic activity. And those are, of course, are the much older ones. So they don't seem to last forever. But they have, this process has seemed to repeat in different places in the planet through time. Yeah.
Are there new islands forming in Hawaii then?
Yeah, there's little new baby over here underwater called Loihi. So if you want to invest in new property in Hawaii, it's going to be a long turnaround time for that. But eventually, if this process still continues, Loihi will be above seawater or sea level, and will be a new island if this process continues.
Where is Yellowstone?
Yeah, great. So you're asking like the perfect questions for like the next slide. So we were looking at a hot spot under an oceanic plate. Now we're going to look at a hot spot under a continental plate, and that's going to be the North American plate. And 17 million years ago, huge amounts of basalt, flood basalts, were erupted on land in North America from vents. These lines here represent volcanic vents, so that's where the lava flows are coming out. And those were mostly along the Oregon, Idaho, and the Washington, Oregon, Idaho border region. And those lava flows flowed downhill because lava is a liquid, so it's going to flow downhill. A lot of them flowed through the ancestral Columbia River and made it all the way out to the coast. But these lava flows covered almost all of eastern Washington and almost all of eastern Oregon. And the Steens basalts are part of them. That, when these were originally mapped, this was thought to be separate from the Columbia River basalts, but we now know through the ages of the rock and the chemical composition, like the trace elements of the rock, that they all are from the same process, and that seems to be a hot spot. So we'll look at that in a minute. What else do I want to say about this? So picture what we saw before. This plume of hot material comes up, and it comes up in this region, southeastern Oregon. And then all this flood of basalt material erupts in southeastern Oregon and along these vents on the Oregon-Idaho border. But the North American plate is moving southwest, and the hot spot is stationary. So we would expect to see then, after the flood basalts, kind of a chain of volcanoes, kind of like the Hawaiian volcanoes, but they might look quite different just because we're in a continent here, not an ocean setting. All right, so 17 million years ago, that's what we get, the eruption of all these flood basalts. And then 16 million years ago, there's these eruptions of highly explosive calderas in southeastern Oregon. And calderas, think of like Crater Lake, so like a depressed kind of cauldron-shaped, feature. But the reason for that is so much magma has erupted so quickly that the top of the volcano collapses in on itself. This is a similar process, but there's no one volcano. It's just this huge area that has this huge magma chamber under it, and the whole area collapses. And instead of being something like 5 miles across, like Crater Lake, they can be 20 or 30 miles across. So they're enormous. These are like the largest eruptions on Earth by the amount of explosive material that's produced. Not by the volume of everything, but by the amount of ash and explosive products. So these are highly explosive eruptions. And as North America continues to move southwest and the hotspot stays stationary, this chain of volcanoes forms across the Snake River Plain in Idaho. And now, as North America has continued to move, the hotspot is stationary. Now the hotspot is over Yellowstone. And notice that just like Hawaii, they're age progressive. The youngest ones are over the hotspot, and the oldest ones have been dragged away off the hotspot. All right, so we could, if we could like get in time machines and travel back to 16 million years ago and go to southeastern Oregon, it would look a lot like Yellowstone today. There would be geysers and mud pots and all the things that exist in Yellowstone, because that's exactly what was happening. The same exact processes that are happening in Yellowstone now were happening in southeastern Oregon. So if we put those together with our pretty pictures, the flood basalts, the initial outpouring of all those basalt lava flows, we see that in the steens. Last time we looked at the steens, we were looking at the blocks, the fault blocks, the range and the basin. Now we're looking at the individual lava flows, all those lines that make up Steens Mountain itself. That's every single time you see one of those lines, that's a lava flow. And those lava flows are just stacked on top of each other, in some cases 3 miles, just stacked with lava flows, because so much material was erupted 16, 17 million years ago at the initial kind of outpouring of basalts. Hart Mountain and Warner Valley, same thing. This is basin and range, but all of those lines in Hart Mountain are individual lava flows of this Yellowstone hotspot. Here we can't see the cliffside itself, but this is Lake Abert and Abert Rim, and we're at the top looking at a piece of basalt that's part of the Steens basalt. Sutton Mountain also, this is Painted Hills here, and Sutton Mountain and the John Day Rivers on the other side of Sutton Mountain, and all of those lava flows are part of the Columbia River basalts. Another picture of Sutton Mountain, John Day. You can see those lava flow, all stacked up. And when you're actually there on the river, it's really spectacular. Again, you can see it there. All right, so not only we were looking at pictures of the basalts, but there's also these highly explosive calderas forming a bunch of ash. And so what does that look like when you go visit those areas now? So this is in the Oahe. The river is cut through some of those volcanic deposits, and you get these very different from the basalt, very light colored, usually kind of golden or tan colored. The chemistry is very different from basalt. These are all a type of rock called rhyolite. And these are the results of the explosive kind of after parts of the Yellowstone hotspot, after the basalt was erupted. Iron Point is another example of that. You can see the river way down there on the lower left corner. And all these, just crazy rock formations in the Oahe Canyon lands. This is all part of those highly explosive caldera eruptions. I think I have a lot of Oahe pictures because they were just...
Have you been down in Hawaii?
Yeah.
Isn't that
It's, if you ever have a chance, do it, because like floating the Oahe is amazing. You're down in these canyons looking up at this rock. All right, so just the last couple slides, we looked at these kind of calderas, these highly explosive calderas going across from southeastern Oregon, across Idaho to Yellowstone. But there are also, this is another caldera, and there are others here, kind of in the central Oregon region. And this particular one that I've highlighted is the Crooked River caldera, and it's about 30 million years old. And Prineville is pretty much in the middle of it, but Prineville is, like if you're in Prineville and you're looking up at the rim rock, that is not the caldera. That's much younger rock. So don't picture Prineville as being in a caldera. It was 30 million years ago that caldera existed, and it's been covered up with much younger stuff. But we do think that there has in the last probably, 20 years or so, this big caldera has been mapped out. So we do know that there was highly explosive activity right here in Central Oregon 30 million years ago.
I heard reference to another PhD, I think out of the U of O, from Dr. Miller, that she did her thesis that the Crooked River caldera was the first. Okay.
Yep, so that's where this is going.
Okay.
That, we don't know that, but that's where this is going. So, question mark, I have a question mark. Is that part of the Yellowstone hotspot? And that's exactly what this PhD student was working on in U of L. Like, is the Yellowstone hotspot much longer lived than we initially thought? We thought that 17 million years ago, with the Steens basalt and the Columbia River basalts, that was the first activity associated with the Yellowstone hotspot. But then these calderas have been mapped, and so it begs the question, like, has the Yellowstone hotspot been around underneath North America for much longer? So what she looked at, and then also if you like keep going, there's Silesia, which is like a flood basalt province. And we encountered Silesia already. It's the pink block that was pushed by the Sierra Nevada block, right? So it formed as underwater basalt lava flows off the coast of Oregon and Washington, and then it was kind of smashed onto the edge of the continent. So now it's here in the Willamette Valley and the Puget Sound. But it formed out here. And that's about 56 million years old. So maybe the Yellowstone hotspot has been around much longer than we initially thought. There was a hand up.
So if you go up to the top of Grizzly Peak
Mm-hmm.
and look around, that looks like a caldera.
Yeah, even from the top of Grizzly Peak, you're not seeing any caldera walls, but you are seeing the outline, the way that this caldera has been mapped, multiple ways, but one of them is when these eruptions occur, all of them, it's the initial highly explosive eruption during which the collapse of the caldera forms. And then after that, there are less explosive, kind of oozing rhyolite flows, kind of like the Big Obsidian flow at Newberry, but much more material is erupted around the edges of the caldera. And Grizzly Peak is one of those, and so is Powell Buttes, and Smith Rock, Gray Butte. So when you're at Grizzly Peak and you're looking out at the caldera, you're never seeing the caldera wall in the sense that you are at Crater Lake, but you are seeing the domes that have been erupted around the edges. And Grizzly Peak is one of them. You're standing on one of the domes. The other way it was mapped is here at Smith Rock, that beautiful golden rock. We'll get to a picture of it in a minute. It looked a lot like some of those pictures of the Oahe. That is the rock that was erupted during that eruption. And it's not just at Smith Rock, it fills the whole caldera, and that's through drill wells. That's actually how the caldera was originally identified, is if you drill down, you encounter the rock of Smith Rock everywhere for like 24 miles by 17 miles. And that's really how the caldera was identified. Okay, so once this was all identified, then people started asking, could this be an older version of the Yellowstone hotspot? And the geometry doesn't really work, right? Like, you should have a chain of volcanoes that are all in a line. And we don't have that here. We have them all in a line here, but then they go this way, kind of a mirror image. So that doesn't really work unless this part of Oregon has rotated clockwise, which it has. We know now that it has. So if you picture, so there it is. All right, so Oregon has been rotating clockwise for millions of years. If you back rotate that, go back in time and rotate it counterclockwise, that could potentially bring these two in line with the rest of them. Does everyone see that? So some people buy that and some people don't. This again is ongoing, like multiple groups of people are studying this, and that idea has a lot of traction with some people but not with others. And it all kind of comes down to not just the rotation, does it put it in exactly, so that the person who has really mapped out most of the rotation says, yeah, that is kind of true, but it doesn't bring it actually in line. It actually puts it somewhere up here. So maybe that's not what's happening. The other real kind of key piece of evidence is the chemistry. The hotspot volcanics, material that's erupted because of a hotspot, has a signature, like a fingerprint of trace elements that says this magma was generated from a hotspot. And that's what the U of O student was working on here, was looking at the chemistry of the rock, and it really does seem to have the signature fingerprint of a hotspot. So these are questions that are still out there. Yeah.
How does the wildcat caldera?
Same thing. So Wildcat Caldera, I didn't show them all, but Wildcat Caldera is here. And then there's also, right around the same time, there was a caldera identified here called the Mohawk Caldera. It's basically in Springfield, just northeast of Springfield. And then, there's thought that there's probably some caldera in the Burns area because there's a lot of the same type of rock that has been erupted. And basically, I kind of joke, whenever people start to look for calderas in Oregon, they find them. So there's probably more calderas that haven't been identified yet. And that also muddies the picture here. If the calderas are actually kind of scattered all over the place, then there's no amount of rotation that you can do to get them to go in a straight line. So there's a lot of questions here still to be answered. But just to put it in scale, I've been saying these are very large eruptions, and to put it in scale, these circles represent the volume of ash that's erupted. So these are highly explosive eruptions, and this is the 1980 eruption of Mount St. Helens. And this is Pinatubo in 1991, and that's Mount Mazama that formed Crater Lake 7,600 years ago. So what we consider to be quite large eruptions are shown on there. But these, what I've been showing you, these other calderas, they are orders of magnitude larger. So all of these bigger spheres represent the volume of these, what are called supervolcanoes, because there's just so much material erupted. So when we were looking at all of these calderas, that's the range that we're in. And a lot of them are Yellowstone, this one, this one, this one. Long Valley Caldera in California is an example. And Toba is the most recent, 74,000 years ago. This is not something that has been witnessed by humans and recorded. Humans were around 74,000 years ago, but they didn't keep written records at that time. And in fact, they and a bunch of other species almost went extinct at that time. If you look at genetic evolution of humans, there's a bottleneck in DNA, which means that DNA was, we had a lot of diversity in our DNA, and then 70,000 years ago, that diversity went to almost nothing, and then it expanded again. So that's called a bottleneck, and it means that a bunch of people died. and archaeologists think that the human population on Earth might have just been a few thousand. And that's probably related to the eruption of Toba. These eruptions.
They could have been killed in that.
Well, they could have been killed in the eruption, but the amount of material that's released into the atmosphere hangs around for a while and cools the planet. And so this actually causes global cooling, and that's associated with extinctions. Or close to, maybe not an extinction, but just things are really hard for a few decades or maybe a few centuries. So we've never, modern humans have never experienced this, but it would be globally changing. It would be nothing like what happened when Pinatubo erupted or Mount St. Helens erupted. Okay, so that's just an aside, and here's the Crooked River caldera here, so you can see it is in the same scale, and this is what it looks like, of course. And that's the rock that was produced during that eruption, and that rock exists at depth throughout that whole area that was shown as the caldera. All right, so you guys are like troopers. You made it through the whole thing, which means you get to take the test. So just kind of summing it up, these processes of subduction, continental extension, and hotspots have created Oregon's high desert landscapes like what we see and know today, but also throughout the past. Subduction hasn't just created the Cascades, it's created other parts of Oregon. Hotspots haven't just created what we see in the Columbia River basalts, but other parts of Oregon as well. And these processes are constant, they're continuing now. And we could see changes in the future. And then I've just really tried to highlight some of the newer research that is still working now to improve our understanding. So thank you so much for making it through all of this. And because this isn't my material, I do want to just put this up. This paper here is the one you mentioned, from U of O, looking at the Crooked River caldera. And then these, Ray Wells is the guy he's a retired USGS scientist. This is the rotation. And basically anything by Ray Wells that you find is fascinating. And then Ray Wells and Vic Camp have done a lot of work on a longer-lived Yellowstone hotspot. They don't think the Crooked River caldera is part of it, but they do think Siletzia is. So that's really great stuff to like dig into if you want more information. Okay.
Thank you very much.
Thank you.
Thank you for your patience. Gosh, hopefully we'll see you next time.
Yeah. No, I'm happy to do it, and I am glad that it wasn't totally my computer. I think we just had to like be patient with it blacking out. And 'cause it did come
I
back.
thought what we should do is set the light, or set the activity on a much longer time.
No, it's
Like
not
an
that, because
hour.
even when I do the mouse, it doesn't